In this video, we're going to talk about Lewis-acid-base theory. And what's interesting about Lewis-acid-base theory is that here we are transferring electrons. On the previous acid and bases we've been talking about, usually a hydrogen has been involved somehow, or a hydroxyl group. Here in Lewis-acid base, though, you actually don't need a hydrogen to have a Lewis-acid base reaction. All you need is something that will accept a lone pair of electrons, which is your acid, and something that will donate a lone pair of electrons, which is your base. And remember from Gen Chem 1, a lone pair is two electrons that are together. All right. So let's take a look at Lewis acids to begin with. So like I said, Lewis acids accept electrons, therefore they are probably electron deficient. That is, they don't have enough electrons. This could be because they're attached to a highly electronegative atom, and that electronegative atom is stealing electrons, or the atom just doesn't have a full octet. And so you need to have an empty orbital, and this empty orbital has to want to accept these electrons to be an acid. An example would be hydrogen plus. Hydrogen plus has no electrons, so its 1s orbital is completely empty. And if you look on BF3, that boron has an empty 2p orbital, doesn't have a full octet, so it would be considered an acid. And a lot of times, highly charged small metal cations, these have empty orbitals, so they can also accept electrons and be considered Lewis acids. And like I said, atoms that are attached to highly electronegative atoms and ones that can have multiple bonds are usually Lewis acids as well. Lewis bases, on the other hand, are the opposite of Lewis acids, so they will donate electrons with another atom. And so these bases must have a lone pair that they want to donate. Generally, anions are better bases than neutral atoms. That's because anions have too many electrons. They have more electrons than protons. They have an overall negative charge, and in general, things want to be neutral if they can, so anions have a lower energy penalty for giving away electrons than do neutral atoms. And usually, if an atom is very electronegative, remember, electronegative means it attracts atoms. So if an atom's electronegative, it does not want to give away electrons. So the more electronegative an atom is, the worse of a base it is, because it does not want to donate electrons. And so in a Lewis-acid-base reaction, what you have is that you have your base donating a pair of electrons to your acid. And a lot of the times when this happens, you get a covalent bond. So here H3N is our base. We have our lone pair of electrons here, donating to our acid BF3, and we have now a covalent bond. This product we call an adduct. And the acid-base reactions we've been talking about in this chapter are actually technically Lewis reactions. And here's just examples of more Lewis acid-base reactions. So we just went over the example at the top. Here's an example where we have aluminum 3+, so it has empty orbitals. We have water, which can donate these electrons. And so you actually get 6 molecules of water interacting, forming bonds with this aluminum to form our adduct. And here's a few more examples. So BCl3s are acid. Here we have an oxygen here, that's our base. You form a covalent bond. Water and carbon dioxide, that will make carbonic acid. So here our carbon is acting as our acid, our water is our base. And then we just have a rearrangement here where this hydrogen can be thought of as an acid. These oxygens, or this oxygen is a base. This oxygen is also this oxygen is an acid here as well because it's accepting electrons. So this hydrogen is kind of working as both an acid and a base, both accepting electrons and donating electrons, and you get carbonic acid. And that's it for this video. I will see you in the next video.